Isaac.
Chandler. Jacob. Austin. Yeah, Zoom. Is that you? Is that you? Hunter. And different Chen. Or Chen. There you go. I'll go over this. Overall, grades are pretty good. But I want to make sure there's no mistake about this one. And then we'll go through the matching, peaks matching. Oh. It's something in my knee. All right. By the way, we're doing great as far as schedule goes. We're gonna take care of the L section matching, and then we get into S parameters, and that's the last section. It's S parameters, so we're doing great. So for the quiz, it looked like this. We had something at a rise time, hold time. Let me actually draw this right. And so it's 0 to 5 volts, so I'll call A 5 volts. At a rise time, tau rise. And then it had an on time, tau. The characteristic frequency, was that 100 megahertz or 10 megahertz? I forgot.
10 megahertz.
So it's 10 to the 7th hertz. All right. That means T is 1 over F naught, or the period is 10 to the minus 7th. And that means because the duty cycle was equal to 1/2 or 50%, that tau was equal to 10 to the minus 7th over 2, or you could just put it simply 5 times 10 to the minus 8 seconds, however you want to do it. That's 50 nanoseconds, right? And I'm going to start with this, just analyze this waveform, make sure everybody understands this. Now, this is important because there were a couple people that completely messed this up, and I thought I went over that. I want to make sure I do. And if you didn't do this in dB microvolts, if you just did it in dB volts or volts, it's fine, but you had to know what you're doing. And I think most of the people did dB microvolts. So if you're doing this right here, the first thing is when we look at just the source itself, we start out, and this value here is 20 times the log, that's a base 10 log, of 2 times the magnitude of A times tau over the period, divided by 10 to the minus 6, because it's going to be in dB microvolts. And is that 134? I forgot exactly. 134. That's dB microvolts. The 10 to the minus 6 here is a microvolt. Whenever you see dB something, it means that something is what you divide the base quantity by. And inside here, these coefficients, if you're wondering where they came from, it's the cosine series approximation where we have 2 times magnitude of C of n, right? And when we do that, this is what we get. So it's going to be that all the way up until you hit 1 over tau times pi, or pi tau. And I want to say that's 6.36 megahertz. Then it starts falling off at minus 20 dB per decade. until you hit 1 over pi tau rise. 15.96 or something, 93? 15.93 or 6?
I kind of rounded, so, yeah, I put on.
15.9 megahertz, all right? And then it starts falling off at minus 40 dB per decade. And this is what it looks like. So first, make sure you have a good picture of the actual spectrum of the input waveform before you do anything. Then when we have the filter, and again, the filter is just a relationship to input output. That's all it is. So when you have the filter here, I have, let's see, for this one, I had a resistor and a capacitor, right? So if I take a look at this, this is V out over V in. So my H here of omega, my transfer function, V out over V in, right here, V source, will just be, I'm going to do the whole thing to make sure everybody understands. The transfer function is really, this is voltage division. It's the ratio of the impedance of the output over the total impedance because they're in series. Now, you can't say it'll always be this because if I had a parallel combination here, then you'd have to find the parallel impedance of those two. And if I had this in parallel with this and I wanted the current through there, you always have to have the transfer function is the ratio of the output whatever to the input whatever. Remember that. Now I'm going to go ahead and do this. So if I put V out over V in here, well, if I want to just do impedances, and I think some people got thrown for a loop here. Let me do it over here. If I want to do impedances, I would say 1 over the output impedance, which is J omega C, divided by 1 over J omega C plus R. Does everybody understand where I got that? There's really no mystery here, but I've got to make sure because some people mess this up. Now, what I do, and you don't have to, but what I do is just multiply top and bottom by J omega C. All right. When I do that, it gets rid of this, gets rid of that, and then it becomes 1 over 1 plus J omega times R times C. Agree? Now, I want to answer this question because I think people had this question just the way they were working. When I want to know what the value of any harmonic is on the output, I can say V out or V out is really going to be Vs times H of omega, right? If I take the source voltage and multiply it by the transfer function, then I get the output voltage. Do y'all agree with that? Okay. I mean, just based on the definition of V out over Vs, if you multiply H by Vs, you get V out. So I come here, and now if I take the output in dB microvolts, so V out in dB microvolts, that's 20 times the log of this quantity, Vs times H of omega, over 10 to the minus 6. Y'all agree with that? Now, when I expand that, I have 20 times the log of Vs source voltage over 10 to the minus 6. And then it's going to be plus 20 times the log of just H of omega, and that's going to be a magnitude. Y'all agree with that? Right? This right here is what we're going to get from this thing. Okay? That's how I view it. Then, when we're at that frequency, whatever the frequency is, then we evaluate this and add it to it. Does that make sense to everybody? Make sure you got this, because you're going to see this again on file. So I'm going to do this over here. We'll put the values in one second. So when I look at my V out in dB microvolts, first, I'm going to find out what my V in is at that, or V source at that frequency. Got it? And it's the ninth harmonic. Since the characteristic of frequency was 10 megahertz, the ninth harmonic would be 90 megahertz, right? So I'm way out here. I'm at 90 megahertz. I should say this is a logarithmic axis. All right. So the paper takes the log. It would be like 10, 100, 1,000, evenly spaced. But you have to have an appreciation. I'm just trying to show you what's going on here. This is 15 meg. This is 90. This is way beyond the 40 dB cut frequency, right? Well beyond it. So now when we get the output in dB, we take 20. By the way, for this one, since tau over t is 50% or 1/2 times 2 just means it's 20 times log of a over 10 to the minus 6. So the first part is 20 times the log of 5 over 10 to the minus 6, and that's the 134 dB microvolts. Then it's going to be, now we're over this range right here. So we take minus, because it's falling, this 20 dB per decade times the log. Now we take the ratio of the upper frequency, which is 15.9 megahertz, over the lower, which was 6.36 megahertz, right? I get rid of the meg. I just leave that on. Correct, class? And the last part, that's falling off at minus 40 dB per decade times the log. Now it's the upper frequency, or 90 over 15.9 megahertz, correct? Now that's how much, that's what the source signal spectrum is in dB microvolts at that frequency. Got it? Now we evaluate the transfer function. We have to add to this plus 20 times the log of the magnitude of that. Well, did I erase it? Of this right here. And the magnitude of this is equal to 1 over the square root of 1 plus omega RC squared. Do y'all agree with that? Just so everybody knows. So this is going to be 1 over the square root of 1 plus, now omega is 2 pi f, and that's at 90 megahertz, so it's 2 pi times 90 times 10 to the 6, right? Times r times c. Was r 100? 200 times, and c 70 or 90 picofarad? 90 picofarad. So this is going to be 200 times 90 times 10 to the minus 12. I'm putting all the numbers in here, and I have to square that. And I'd suggest one other thing. When you do this on an exam, a final exam, make sure you show the steps. Because if I just see this and an answer, and it's wrong, and I see no work to support it, you get no extra credit. All right? So you got to help me help you. Because if I don't know what you're doing, and especially because kids, I hate to say this, try to bluff. They say, oh, I meant that. No, I always assume the wrong thing when you try that. Just be clear, and I'll help you out if you make a silly mistake. But you all agree with that? So you go ahead and crank the numbers. I want to say this is like minus 20. That number right there, I forgot exactly. Just right here. This, I think, is about, but I'm not sure, minus 17 something, I forgot.
Minus 19.
Yeah, it's close to 20. This is about minus 19.18. And the rest of it, I forgot what it is, but I wanted to make sure you understand. That drops it down almost 20 dB more, that filter. That's the only real thing you're going to get out of this right here. That filtering is going to bring it down by 20 dB that high up, which isn't a lot. Anyway, the overall answer, now I put this up, didn't I? The solutions. All right, what is it? Because I don't remember.
76.
Yeah, that's right.
75.
76.75 approximately dB microvolts. You're going to see dB microvolts is used extensively in industry. You have cell phones, right? I haven't done this in a while, but you can go and actually see what the power level is that your phone's receiving from the nearest cell phone tower. And it will be not in dB microvolts, even though you can look at that signal strength, but it's usually in dBm. Do you remember dBm is power, right? And it would be the power the phone's receiving. It's not the power density. It's the power the phone's receiving. And then it's divided by 10 to the minus third, and it's 20 times the log of that. And it will be, believe it or not, like minus 80 to minus 100 dB, or dB milliwatts, pardon me. I said dB milliwatts. If you don't believe, if you have a cell phone and you get it out and play with it, you'll see this. Now, sometimes it's useful to do that. You know why? Because there's a signal strength threshold where your phones won't work. And it does depend on nearby interference sources, but typically when you get about 100, minus 100 dBm, forget it, about that level on phones. Has anybody ever looked at this on your phone or any other thing? I'm almost tempted to try it on mine. I haven't done this in a while. But I know almost all cell phones have the ability to look at the power that they're receiving from the nearest cell phone tower. And I did this with one class, and I don't know if you guys know this, but downstairs, cell phone reception used to be terrible. I think it's a lot better now. And they could see the difference. If we were upstairs and they took a look, and going downstairs, the cell phone signal basically goes down to just about zip, minus 110 dB, and they couldn't hear dBm, they couldn't get it. So that's the quiz in a nutshell. Now, do you have any questions about this? Trying to make this straightforward, and listen, here's one piece of advice. Do your homework, and if you have questions, ask me this last closing week or two, week and a half. Because you don't want to get in a position of having to catch up and cram in this last part of this course, because it tests parameters, and people really get lost. Okay, so now for the homework. Do you have any questions? Okay, nothing. Jacob, you're shocked.
You're gonna go more in depth on the different cases, right?
Yeah, but I wanted to know, did you try?
Yeah.
All right, it's pretty straightforward, right? And again, I'm just gonna mention this, it's not tough. If you haven't done it, please do it and because you don't want to cram for this, you really get yourself in trouble. So whenever we do impedance matching, I'm gonna just show you the Smith chart first. This is my Smith chart. Oh,
Could you post that?
did I email? I didn't. Doggone it. I'm going to do it right now if you don't. Jacob, send me an email. Or anybody here, send me an email. That rotated Smith chart, I'm so sorry. I'll send you one. And the rotated Smith chart, if you look just rotated Smith chart online, I don't know what you're going to see. I'm serious. I don't know if it's out there.
You can find like one or two, but they're not PDFs. Like you can't print them out because they've got like work on them or whatever. So.
All right, I will give you some. You should be able to get one from if you go to HP's Hewlett Packard's website, but I don't know that for a fact. I have some. Send me an email. I usually send everybody one a PDF form. I'll post the PDF and post that so you can print them out because it's not. Did you all try that though? All right. It's not hard to do this, but you get hammered if you don't do it and you try to play catch up, especially when you get into S primers. So anyway, this is my Smith chart. Please, as many people as want, send me, Dr. Baginski, send us the rotated Smith chart. So here's the rotated Smith chart. Right, like that. And this is 0, this is infinity. This is the R=1 circle. That's the rotated circle. And it's important because any point on here corresponds with a conjugate point here when we do 1/. So when we do impedance matching in general, if we have a load and a characteristic impedance and we want to match it, our choices are this. The first one is if the normalized load falls inside the 1 circle. So this is case 1. And it would be normalized impedance is going to be inside 1 circle. That, the only thing that means, by the way, is that the real part of the impedance is less than 1, the normalized. All right, because R=2 is here, R=3 is here. That's the only thing it means. You could just as well say real part of ZL normalized is greater than 1, and it's the same thing. So then you have to go to the admittance domain. So for here, this is your first point. We have to go here to your second point. And then I'm just going to assume we go this direction. We don't have to. We could go this way. But here you're moving along a contour of constant real value. Do you all see this? You're adding a plus j. This would be adding a plus jx, but it would be an admittance, not an impedance. Maybe call it plus j. No, I can call it x to this point. This would be 0.3, right? And then from here, you would move to the conjugate point. You'd move to the conjugate point here, and this would be 0.4, right? Well, here I came in here, took 1 over that. I didn't really move. I just, now looking at the admittance, right? This is ZL. This is YL. Then I get rid of the imaginary part. Now I'm here. Then I go from the admittance domain to the impedance domain. I have 1 plus j something. I'll just call it x here. Call that x. I guess you could call it y. It doesn't matter. And now what I'm going to do is add a minus jx to get back. So first thing I have, I guess Dr. Wentworth uses a b here, now that I think about it. So first thing is I'm going to add JB to this, and then the next thing I'm going to do is add an impedance here that's going to be minus JX. Actually, this is a minus JX here, so it'd be a plus. This would be a plus. Y'all follow me on that? That's for the first case. The second case is, so this is ZL inside. That's case 1. Case 2 would be normalized ZL inside the rotated chart. Inside rotated circle. So now, y'all follow me on this one? So I'll do this one over here. Something like that. All right, that's the R=1. And that's the rotated circle. So now, if my ZL lands inside there, remember the real part is much less than 1, right? We're way up. But we're on this, I call it a line. It's really this contour for constant value of R. This is just R something, right? Now, this right here is going to have R plus J, doesn't matter what you call it, J alpha here. I can add a plus impedance, which would be adding an inductor, right, at J omega, and I could get to this point, right? That's where it would be nice, right? Or if I wanted to in series add a minus J something, I'd add a series capacitor and I could get to this point. Does that make sense to everybody?
Mhm.
And I'm going to give you a piece of advice. Most of the time in series, an inductor is great. And the reason is because there's DC biasing often in circuitry. And often at times when you do this L section matching, it may be something that goes in parallel with an output antenna, but it might have a circuit next to it that requires a DC offset. So I always allow the inductors to go in series, and Whitworth's book, he brings that out, because an inductor has zero impedance to a DC current. And remember, a lot of times with your BJT amplifiers, you always had to get those either self-bias, either with you had to get a resistive bridge so that you could self-bias the circuit into the point where really you could do a maximum output voltage swing, right? You wanted to get the output voltage about half the maximum swing possible. Do you all remember doing this stuff? And then your output, usually your output devices was linked by a capacitor, as well as the input signal was linked by a capacitor, stopping DC. Y'all follow me? But when you're dealing with microwave circuitry, oftentimes it's very possible that you can feed an actual BJT amplifier with one of these things. You need an L section matching, and you're going to have a microwave link there with DC bias. So an inductor in series is good. That's my take. Anyway, I can add something here, which is a series. So for this one, what you get is this. You're going to have ZL here. And then normalize ZL. And then you're going to have some series impedance. I show this as an inductor right here, but some JX in series. Now, once I come to this point, so here's point 1. This is point 2, correct? Now, you shoot down here to the conjugate point. So this was Z, now this is going to be Y, right? Which is 1 over this Z2. Call this point Z2, right? Now that's an admittance, right? Now, if it's an admittance, and this is something to keep in mind, I've got a negative J something here, right? And I want to get to this point, and so I'm adding a positive J something, right? And that would be a capacitor, right? An admittance, positive J, correct? Y'all follow me on that, class? If we do one, you don't? Does anybody not follow me? Do you? Okay, remember that. Admittance, right? The inductance, if you add it, would be a minus J. The capacitance would be a plus J, because admittance is 1 over impedance. And then you would add a plus J value until you got right here. So here, you're going to have some plus J, and I'll just call it B. And then it's matched, that one frequency. Now, finally, the thing that's important is, well, what if you're outside of either of them? Then it doesn't matter. And I'm not kidding. If your point, and just follow me, suppose I pick a point right here. Here's where I come in. Well, let me go ahead and draw this, because I want to make sure you see this. To me, it's kind of interesting. All right, that's R equal 1. That's the rotated. Suppose I'm out here, and I'm going to try to show you the trajectory in one of these field lines. Say, or these lines. Say it's R equals 0.3. Okay. And make it 0.3 J1. That's here. So my normalized impedance, because this is J1 right there, is going to be equal to 0.3 plus J1. 1. Y'all follow me? Now, just follow me on this. Remember, by adding J, I can move until I hit here, right? Y'all agree with that? That would be an impedance, correct? That would be a series impedance. I can hit this point, and then I can go from this point to the admittance domain, right? I can go from here, by adding impedance here, that's in series, then taking 1 over that here, now I'm on the rim, that's admittance, right? And then I add a plus J admittance to get to here. Y'all follow me? Series impedance, and then shunt admittance. Or, now just think about this. This is the thing people get in trouble with. I don't ask you usually too many questions about this. Or instead of doing it in the impedance domain, now follow me. I'm going to go to the admittance domain. If I go to the admittance domain, basically I take 1 over this, right, wherever it is, right? This would be the admittance domain. That's not exactly drawn right, but you all follow me, right? So now I'm in the admittance domain. And look, in the admittance domain, I have a real part. I'm on a trajectory, not that trajectory, I don't believe, but a trajectory. Y'all follow me? It's got a real part, right? So if I add a plus JY, that's a parallel item, right? I could land here, correct? You always go into this point. Y'all follow me? Because remember, these trajectories are always greater than or equal 1. You can't get to that point. Y'all follow me in that class? Jacob?
When you get a C there anyway, when did you get a capacitor in both?
Yeah, but I'm just talking about you're adding it. Here, your impedance, right? That's where I came in. 1 over that's admittance, right? Now I'm going to add in parallel, not series, right? Because it's an admittance. So I'm going to add in parallel or shunt and admittance till I get to this point, right? Or I could get up here, either one. I could go here or here, either one of those, but I need to add an admittance, a positive J, which is a capacitor, right? But it's in parallel, right? So I can get to this point or this point. Then when I'm here, I go to the impedance domain, and now I add an impedance. Y'all see that? So when you're outside the rotated circles, either the 1 or the rotated circle, you can do it either way, but you got to know what you're doing. And here I can get 2 capacitors very easy. Sometimes that's useful. And I don't, when you have FETs, front ends, an FET is an oxide layer, a field effect transistor has an oxide layer, a metal gate, and then you pull up a channel, right? Or if it's depletion mode, you actually get rid of the channel, you pinch it off. But anyway, you have to get it out of the saturation mode or into the active mode. All right, you do it one way or the other. And that's by a voltage on the gate, right? So usually you want, not always, usually you want a DC bias possible if you're feeding, like if you have a microstrip circuitry, feeding an FET amplifier or a BJT amplifier, you want to make sure you can have DC bias. So you would want an inductor in series. Do y'all follow me? So based on that, if I came in here and I wanted to add admittance to get to here, remember, actually, I should show you this. This is the way the admittance things look. That's J1, J.5, and so forth, right? On the outer edge. So here, if I have 0.3 plus J1, I would want that J value to be reduced to hit this, right? So I'd be adding a minus J something, right? That would be a capacitor, wouldn't it? And if you don't want a capacitor in series, then you would go to the admittance domain and you would have a capacitor in parallel. Do y'all follow me in that class? And then you could get to this circle and then from here, go to here, and you can mess with. But I'm just going to tell you one thing. With these things, the key is if you want inductor or capacitor in series or parallel, it's in the beginning. If you wanted, and if you didn't want it, obviously, if I'm moving from here to here or here to here, I'm going to be adding something that's going to reduce this value, or it's negative J, correct, class?
Mhm.
If I'm adding a negative J, that's a capacitor in series. And if you don't want a capacitor in series, then go right to the admittance domain. Now when you're here, the key is this. If you're in the admittance domain, I can get to this point or this point, correct? But if I wanted an inductor in series, I'd want to go to this point, all right? And the reason is because this is 1 plus J something, right? I mean, it's not 1, but something plus J something. When I go here, I get 1. If I'm going to get on a 1 circle here, 1 minus J something. If it's an impedance, I'm adding a plus J, which is an inductor. Y'all follow me? So your impedance element would be an inductor if you land down here. All right, so I'm just trying to make sure we're clear on that. And you play with these problems. I gave you a fair amount of problems, right? I think I did. I didn't give you the thing. And you're going to need a compass and you're going to need a straight edge to do these. Well, really you need a straight edge more than anything. But a compass is useful too, I think, at times. They're not hard problems, but you have to know what you're doing. So I'd like to do at least one that we haven't talked about. You want to pick one for me, Jackie? You seem to have a knack for asking interesting.
I had a question.
Go ahead.
Does the order of the shunt or series?
Absolutely. Right. Because if you don't put this in parallel with this, if you put this in parallel over here, then it's a completely different problem, right? The first thing is you're adding something in parallel with the load, right? So you get to the rim, right? Now when you're at the rim and you add this, then you get, you match it.
So the first distance that you move is the thing.
You're not moving at all. These are connected right to the load.
Right. I'm talking about on the Smith chart. The first distance you move to reach one of the edges, that change is associated with some element.
Right. If you're,
Closest to
remember,
the
when
load.
we go in, we're in the impedance domain here, right?
Right.
All right. Anything we add is in series here, right? If we stay in this domain and move. But if we say we don't want to work in the impedance, we want to add things in parallel, then we take 1 over that. And now we're in the admittance domain, right? And now anything we add is going to be in parallel. Y'all follow me? All right. So if we go to admittance domain, add something in parallel, whatever this corresponds to would be the element in parallel, that JB. Then from here, and actually you'd want to move to here if you want to inductor in series. Now, right, I'm in the admittance domain, I go back to the impedance, I have 1 plus J, or 1 minus J something, and I add a series inductor. But this is important, the order is critical. If you put this first in this, then it's not matched at all. As a matter of fact, it's a disaster. Clear on that, class? Oh. Do you have a question?
I think it'll all get cleared up if we do an example with actual numbers.
Remember that if you're going to go shunt, if you're going to admittance, you're always putting in parallel. If you're impedance, you're always putting series. That's it. That's it in a nutshell. Okay. Now, an example. Jacob, since you haven't come forward with one, do you have one? You? No? You want me to do one?
Someone could just pick one out.
Yeah.
Unless they, I pulled the problems, but
Bomb. Aye. I want to do these at least one more before, and I'd like you to help me out with this.
Um, 10.14,
Yeah. Okay.
design L section matching network matching 80 minus J50 load.
Hold on for 1 second. Let me write this down. So ZL is what?
80 minus J50 ohms to a 50 ohm line. Design, determine specific value.
All right, this is kind of a redundant thing. You know why? Because the normalized impedance will have a real value greater than 1. It'll be inside the 1 circle.
Yeah.
I'm looking for something besides that.
Okay.
How about, I mean, I can make this up. If you guys are willing to do this, I'll show you. I'll need some help though. Do you have, anybody have a rotated Smith chart here? All right. Well, there's one in. That's all right. We can do it anyway. Yeah. So. All right, look at one. I gave you, do you have access to the solutions in your book? I mean, in that I posted. Give me a problem. Give me like 10, 16, or 17.
10, 16 was 20 plus J 50.
Perfect. 20 plus J what?
50.
Excellent.
50 of one.
All right, Z naught's 50. This is perfect. So this is ZL. All right. I have my ZL here is 20 plus J 50. My characteristic impedance of this line is equal to 50. Therefore, the normalized impedance is equal to 2/5 plus J1 or 0.4 plus J1. Now, you have a Smith chart. .4 plus J1, well, this is the one circle. 0.4 is something like that if you look at it. This is R equals 0.4. And J1 is right here, it's the North Pole. So there's going to be your first point is right here. You all see that? You go ahead and, I mean, do you have access to any kind of a Smith chart you can view on, in Whitmer's book? He has a Smith chart. I know he has one in chapter 2, but it doesn't have the rotated circle. I'm just trying to show you, this point is outside of either circle, right?
Mhm.
And what else does he ask in this one?
For design of the L section matching network, you know, just like load impedance lines like this now.
No, I mean, what does he say about the, does he want an inductor in series, or does it say anything like that? Is that the solution of the problem? You know?
It's bit from the solution, but it doesn't really.
Well, the real thing is, if you want an inductor in series, that's the key.
It asks for all 4
Oh,
processes.
okay. We're going to do 1 of 4. Right? All right, now you can see it looks like this. This is the rotated circle, right? So this is my point 1, and I've got a value here of 0.4 plus J1. All right. Now I'm going to talk my way through this one. If I add an impedance, it's going to be a capacitor. Because that's J1. To get to any part on the rim here, this is going to be like J 0.3, something like this would be the trajectory. So that point, because I want to get to the rotated circle, that means I'm adding a negative J something, right?
Mhm.
In series, and I don't want a capacitance series, if I can help. Now we can if you want, because Wentworth says he wants all 4, but I'm going to get the one that's actually probably most useful. So I go from here to point 2, which is 1 over that. So now my point 2, YL, is 1 over that, ZL, and 1 over 0.4 plus J.1. Can somebody just give that to me?
I'm getting 0.34 minus J 0.3. 0.86.
Anybody confirm that? Okay, good. So that's my Y low. That's close to 0.4, by the way. Right? 0.4 was up top, right? It's close. All right, now I look here, and what I want to do is move along this line right here that's 0.34. So what I really want to do is move, remember I can't draw that well, but this is the 0.34 real part line. And I want to move from here, this is 0.2 to 0.3 here. Unfortunately, if you look in the solutions, he'll give you that value. But if you have a rotated Smith chart, you can do this very easily. As long as you have a sharp pencil to plot these points. What can you give me? It's going to be something of the order of like, it's 0.34 for sure, and it's J something, because we got to get the difference in J values. This is minus J 0.86, and we're going to get here, so it's minus J point like 4.6, something like that. Take a look at this point right here.
It doesn't, it just has a B.
What does he add to it? What does it say?
I could be reading, but it doesn't.
All right, it's all right. Well, here's what happens. That's 0.2. It's going to move here. So whatever this is, you got to take a look at the J value here is 0.86, right?
Mm-hmm.
What we have to do is add to that a J value to get on the rim of this thing. So do me a favor. Oh, if you had a rotated Smith chart, you could look at 0.34, the real part, and you could see where it intersects that rotated circle.
It's kind of 0.1.
I'm sorry?
Yeah, I say it's kind of 0.5.
Yeah, about 0.5.
J
For the
minus J 0.5? Is that right? All right, so this right here, this 0.3 is going to be Y equals 0.34 minus J 0. Say that again?
0.5.
0.5?
Yes.
Okay. All right. Now, the nice part is this. I've got to see how much I've added to get to there, right? So if I just take 0.86 and subtract 0.5 from it, 86 minus 50, right? That's 0.34, isn't it?
Mm-hmm.
Right, so it's J 0.34. So I added in series for this one, this is going to be normalized, a J, you know what though, if I want an inductor, I don't want to end up there. I want to end up here. So that's not going to be, if this is 0.34 minus J 0.5, this point up here, I want to move all the way up here, will be 0.34 plus J 0.51, right? And I want to move to there because I want an inductor. Wait a second. Yeah, we're in the admittance domain. So that's my 0.2. That isn't 0.3. I'm going to move all the way to here. Here's my 0.3, and this is the value. Right here. So that means I have to add,
Should just be 1.34.
well, I'm going to go from, that's going to be 0.3 plus 0.86, or 30 plus 86. So it's 1.12, isn't that right? Hold it. I need to move from here to that point, so I need to add something to x plus 0.86, or minus 0.86, pardon me. I need to say this is an admittance, so B minus 0.86 has to be equal to 0.5. So 0.5, 50 and 86 is going to be 1.16, right? Isn't that right? So that means I have to add here a J 1.16. Y'all follow me? If I'm here and I have minus 0.86, what do I add to that to get to 0.5?
I think,
Right?
I think it's 1.34.
Three.
Did I mess that up? Oh, you're right. You're right. You're absolutely right. Absolutely.
36.
3.4.
3.4, sorry.
Because
My
all we
bad.
did was add one more than where we were before.
Yeah. 1.34, my bad. Right?
Yep. So,
Now, if you do this, not at this point, take 1 over that. We should get about 1 plus J something. That's 0.3. This will be 0.4 here. And this should be 1 minus J something. Sorry, this is an admittance. I got this as an admittance. I'm so sorry about this. This is 1.34. That's an admittance, my bad. Now here is going to be the impedance. What is this value? My knees bother me. Just take 1 over this, 0.34 plus J 0.5 and tell me what you get. The real part should be 1.
Let's do it. That's what it's saying.
And what do you get for the imaginary?
1.36.
Minus.
Yes, sorry.
Minus J, 1.36, right?
Yeah.
That means we have to add an impedance that's J, an impedance of J 1.36, correct? Now, we might as well get the values for this, but this is a good thing. It exemplifies the way to do it. And again, it's 1 of 4, right? Because we're outside both rotated circles, so we can do it any which way we want.
Mhm.
All right, so that's an admittance. That's an impedance. And I'm going to erase this and go ahead and calculate the values. Does he give an operating frequency for this problem?
2.5 gigahertz.
Okay. So here we have an operating frequency of 2.5 gigahertz. By the way, that range right there is so typical. Wi-Fi is what, 2.45 gigahertz, right? Anywhere around 2 to 3 gigahertz range, cajillion tons of stuff you do in engineering in that frequency range. Up around 10 gig, you get lots too, and then around 33 gig, and now 77 gigahertz for automotive radar. So that kind of microwave frequencies are very common. Anyway, 2.5 gigahertz is very common. So we're going to deal with this one first. This is an admittance, so we need a J 1.34, right? The way I normally do this is say, if I have two elements, I have inductors or capacitors. I know for sure that's going to be a capacitor, but I do it this way. I start with capacitive reactance as 1 over J omega C. This is the way I'm just showing you to do it. Then I normalize it. To calculate that value of capacitance, it has to be normalized. So I divide this by Z naught. Now I have the normalized capacitive reactance, but I want the admittance, so I take 1 over that. So then I find the value of Y is going to be Z naught divided by XC, or it's simply equal to J omega C Z naught. And I set that equal to the value that I need here. Y'all follow my train of thought on this? So that's equal to 1.34, J 1.34. And that means the value of C is simply 1.34 divided by Z naught, which is 50, divided by omega, which is 2 times pi times 2.5. That's 2.5 times 10 to the 9th. And that'll be the value of capacitance. And looking at that, that looks like it's picofarads.
It is. Solution.
What did you get?
Solution say 1.69 picofarads.
That's very small.
That's what I get. So,
1.69 picofarads. I'll tell you how small that is. Your wire length can change this capacitance from 0.69 to 0.79 just by a small amount at that frequency range. I'm going to say that is not much capacitance. You breathe on it, it'll change. I'm just warning you, when you're working around these things, it's good to have a feel for how sensitive the part is to lead length. This thing's going to be very sensitive. 1.69 picofarad is not much at all. All right. Next, we're going to get the inductor. So that's J 1.36. Is that what he had too, by the way?
It doesn't say.
He should. The capacitor?
Yeah, for the capacitor, no, sorry.
Is that right?
Mhm.
All right, now for the inductor, first I take a look at inductive reactance. That's J omega L. Then I normalize it. Now that's normalized value, and I want it equal to this. So I just set it equal to, but you gotta normalize always. And you can see L is equal to 1.36 times 50, right? Divided by 2 pi times 2.5 times 10 to the 9th. That's, looks like nanohenries, is that right?
It's in nanohenries, 4.5 nanohenries is the solution.
I want to tell you something, that's small too. I don't know if Stu chose these numbers on purpose to show you these things. That's a reasonable value, but when you're dealing with stuff that small, spend some time, get on YouTube and talk about, and look up on YouTube or just Google it, high frequency engineer. You have to use dielectric screwdrivers. You try to get those lead lengths as absolutely small as possible. And the last trick I'll tell you, in case you ever have to build these things, anytime you can get a variable value for capacitor or inductor, use it. That way you can tune it. Because even when you put the whole thing together, the stray inductances and capacitance can change that frequency. So you usually give yourself a little breathing room so you have a little bit of a tuner. You all see these little pots? They're usually square. They look like a cube, and they have like an adjustable screw on top for variable capacitors. And you want that. You always want breathing room, because I tell you one thing, when you deal with high frequency engineering, I think I told you a story. We took a ham radio, or we took a CB radio and turned it into a ham. Talk about a nightmare. Your hand goes near there and the center frequency shift is. So we always had I learned this the hard way. Anytime we could put in a variable something that we could tune externally with the dielectric rod, we did that. The dielectric screwdriver, huge difference. And we had one guy who knew how he had some experience in the real world that was helping us, and that was nice. Okay. I can only tell you this. I'll give you a few more problems. I'll send you that rotated Smith chart so you'll be ready. You want a quiz Friday or Monday? Either one. Friday is going to be this, all right? All right, it'll be on this. All right, now I'm going to just show you the beginnings of S parameters, okay? This is really, we do S parameters, and this is all microwave engineering. You're going to use this stuff probably. You have to be exposed to it. I want to ask this. Has anybody here done anything with microwave engineering work, gigahertz range work? It's very common, and nowadays with Wi-Fi and all the cell phone towers and stuff, some of you I know here, I mean, I bet a lot of money on this, you're going to be working someplace where you're going to have to use S parameters. Have you had S parameters yet? You had ABC parameters or H parameters, right, for your FETs, or
Yeah.
you had HFEs, the forward gain, right?
Oh, yeah.
All right, they're parameters where I got a real education on this when I was at NASA, and we were doing stuff where we had to use network analyzers, and everything's in terms of S parameters or ABC parameters, ABCD parameters, or H parameters, and all these things have their usefulness. So when we talk about S parameters, what we're really doing is looking at a block diagram type of thing where we're going to have something. This is really it's going to be a transmission line. This is going to be port 1. It's got some characteristic impedance. It is a true transmission line. And this is going to be something that's attached to something with what's called S parameters. And this is going to be port 2. Has some characteristic impedance Z0. And you're going to have to follow me on this. Since we're talking about transmission lines, and we are when we do S parameters, we've got something propagating this way in transmission line on the first one, port 1. It's something reflecting. All right. So they take a look and they talk about the incoming voltage waveform. They call it V1 plus. I'm just showing you this in a bulk manner. There's also going to be a reflected voltage called V1 minus. That should make logical sense to you. We know the relationship that V1 minus V1 over V1 plus is the reflection coefficient. But for now, leave it at that. Here, I'm also going to have a V2 plus, and I have a V2 minus. The minuses are always going away. All right? Pluses are always going towards that block there. Got it? Now, the relationship between the ports is the S parameters. And it says this, V1 minus is equal to V1 plus times S11. Actually, yeah, let me do it this way. It's S11 times V1 plus S12 times V2 plus, and V2 minus is equal to S2, let me get this. Now this will be in your book. And you see it in your book?
Page 5.
Page 558. All right, a lot of times they'll do it like this. They'll put blocks or they'll put brackets, something like this. And the reason is this is a 2-port. There's only 2 ports. There's 2 ways for information to get in and out of this S block. Now, and the truth is this, you could have N ports. You could have 3 ports. You could have another port here. Things coming in and coming out. Follow me? You can have as many ports as you want, but you always start with 2 ports. And a 2-port device is very common. The S parameter measurements they do are over the frequency domain. And we look at what these actually mean. The S11, S12, then we do an analysis of some very basic circuits, and then you get a good feel for it. A lot of times this is used to get amplifier gain characteristics and stuff, but for now, I just want to show you this. So what is S11? Well, it's really a ratio of V1 minus over V1 plus, assuming that V2 plus is 0. If you look at this, if you ignore that, S11 is really V1 minus over V1 plus. If this is 0, right, and it's, in other words, there is no wave coming in here, so this component will have no effect. Follow me? If V2 is 0, this part doesn't have an effect. This is a reflection coefficient. I mean, that's really the reflection coefficient at this port. You can put it down. That's typical. And I got to spend a little time explaining. Likewise, S22 over there, I'll put it here. S22, oh my. No, I'm not over yet, right? I got to throw it to
You got 5 minutes.
S22 is equal to V2 minus over V1 plus, assuming that V1 plus is 0. Just look over here. V1 plus is 0. It's got to be, right? And that's really the reflection coefficient. I'll just call it gamma 2. It's the reflection coefficient at port 2. And it assumes, now I got to tell you one other thing. You see how I said here that for S11, assuming V2 plus is 0, I want to make sure you see one thing. In order for that to be the case, that's a transmission line, right? Well, if you had a short there, then the outgoing wave here would reflect back. And the way we make V2 plus 0 is we put it into a matched load. So it's into Z0. It has to be so. If anything gets through this port, it won't reflect back, in other words. Do y'all follow me? So whenever we're doing S11 and S22, it's assuming that there is no reflection back from the other port. Then, when we take a look at S21 and S12, they're called the forward and reverse voltage gains. So when we look at S21 here, right here, that's V2 minus over V1 plus, right? Assuming V2 plus is 0, isn't it? Isn't that right? Now, what is that really? When V2 plus is 0, well, it's the ratio of output voltage to input voltage if this is into a matched load. That's the forward voltage gain. Write that down. This is the forward voltage gain. And they measure that all the time. I mean, when they're doing it, they analyze amplifiers and stuff like this, they'll sweep the input frequency over a range at a constant voltage, and they'll look at the output voltage, and they'll get the S parameters, the forward voltage gain. This is the 2-1. They'll get that over the range of frequencies that they're of interest for the amplifier. That's real important. Does anybody here ever do you have high fidelity audio anymore? I know there's, what is it, surround sound 5 channels. Anybody have anything like this? You ever read the amplifier specs? They'll have like frequency gain, and they'll have intermodulation, interharmonic distortion ratings and all that. It used to be when you were long ago. Oh my God. High fidelity sound was really people had, that's how far back it is. They're called LPs, long playing albums. They were vinyl, they spun. You ever see these things? No. I mean, it's long gone, but back in the day, that was the best sound you could get. We had turntables that cost a fortune. People would spend a fortune. Then I was an electrical and computer engineer. You know what helped? When you're that, you build stuff dirt cheap. Pennies on $1,000. Literally, we could build circuitry. You go downtown and buy, be $1,500, $2,000. You can build it for $20. It gets very appealing being an electrical engineer when I was with you, because you can make some really nice stuff very cheaply. The problem is speakers. They cost a lot of money. All right. So anyway, that's the forward voltage gain, and the reverse voltage gain is really what? V1 minus over V2 plus, right? And that's saying this is gonna be with V1 plus equals 0. This is the reverse voltage gain. You don't want this. This is bad. All right, you prefer not to have anything gaining. I mean, you would like this to be 0. All right, that's the way it's generally. So that's what it is. What I was gonna do, I'm about out of time. I'm gonna next time do this. I'll take you through, maybe we do one more of these L-section matching now that I'll send you a Smith or a rotated Smith chart. And then, do you have a question?
Yeah, is S22 supposed to be V2 minus over V2 plus?
Yes. I can't believe I did that. Thank you. Yes, sir. I'm sorry. This needs. I'm trying to do something for it, but it's been bugging the heck out. Here's the one thing. I plan next time to do one example of S parameter matching. I'm going to give you, I'll send you the link and bring a few of these rotated Smith charts with you. And a pencil and straight edge. You can bring a compass if you want. And then I'll give you some homework on S parameters. I won't give you a quiz on it. And if you have questions, please let me know. Now, if you look in that chapter, the S parameter stuff, we're going to spend about 2 or 3 lectures on that. And then we go into some of the typical filter design, and then we're done. All right, we don't do microwave amplifiers here in the true sense. I think you do that. You had analog already, right?
Mhm.
Did he do microwave amplifiers or anything like that? Or he did FETs and he did BJTs, differential amplifiers, Darlington pair. Did he do Darlington pair? He did followers, emitter followers, common base circuits, right? So he did, and common gate, he did the basic circuit configuration. I don't know, you get an RF course at all? Well, when you get high frequencies, and I don't know if you covered it in your basic course in analog, but then what you typically get is the classes of amplifiers. There's class A, that's a linear amplifier. Class AB, it's one that's gonna have cutoff. And then class B and class C, do you all remember those?
But it's just someone in RF lab.
You've had RF lab?
Mm.
Whitworth or who?
Woodward.
All right. Well, those things become very useful bits of information to know. And then the high frequency engineering, you'll have a microwave feed like on an FET and stuff like. Did you do that? If I can, I'll show you some stuff that I think is useful. All right. And if you have questions, just ask me. Sorry.
When's the final for this?
I can